Hi everyone! Today we are going to build an exciting project with Python. This is a library chatbot that uses the retrieval augmented generation approach. This means our chatbot works based on OpenAI models while retrieving up-to-date information from our knowledge base. In our case, library catalog. We will look at tips to make this project easy and quick using Langchain tools. Our chatbot will find books by context or details, but only from our catalog. It will also use past conversations to make its answers more relevant. It will handle unstructured questions from the users, understand what the user wants, find this information in our catalog, and still provide clear, related answers. We will try two ways to do this. Using similarity search, vectors, embeddings with Neo4j to find related information, and using Langchain to generate cipher queries for our database. We will use an agent to help our bot decide how to search information optimally to find what we need. It might seem a bit tricky now, but by the end of the video, you will be able to do it easily. Let's start. So we will start by deploying containers locally for our project. I'd like to share a link to the Docker website where you can learn about containerization if you're not yet familiar with this. There you can find a section with detailed instructions and presets for containerizing various AI-driven projects. This means you don't have to create files from scratch, but can choose those closest to the project you are implementing. In our case, it's a chatbot project, for example. I based my work on these files and made only minor modifications. Let's quickly look at them, but we won't go into too much detail. We have three containers here, one for our future application, a second container for our database, and the third container I created and placed a pipeline into for uploading information to the database. The directories where the Docker files for building the containers are located are specified here, as well as the ports. We keep all secrets in an yen file. You will need a key for OpenAI if you use OpenAI like I do, but Docker's instructions also provide information on how to use three models. So it's up to you. The yen file looks like this. Here I also have variables that point to the models and functions we will be using and discussing further. I also use volumes in my compose YAML file because I want changes I make locally to be immediately visible in real time. The order in which we read the containers is also specified. Here you can see it. And what's really important, that for the database container, we use the Neo4j 5.21 version because it includes the latest features related to vectors and the indexing. If you follow the Docker instruction, it uses an older version, so pay attention and change that. We might also need the Apple plugin for some cipher queries, so I did this here. And here is the health check configuration to ensure that our services are running as expected. And here we can see the Docker files almost unchanged. Comments have been left in the files to explain what's happening, and the link to the GitHub repository is provided under the video. So now we can build and run our containers using this command, and we are ready. So the next part is our database, which we can also refer to as our library catalog. Remember, we need it so that our bot can use and search for information, especially within this library knowledge base. First step, finding the right database. We will see the link to the one I used, and I've attached it in the description below the video. Our dataset includes essential information: book titles, languages, publication years, summaries, author, and genres. Now let's see how this information will appear in our database after we upload it. I can use the admin.zo browser version from Neo4j and use this port for connection. And we use Cypher language for our queries. So we find any 10 first results from our database. And here's a note for a book with its details. Here are the other notes, the author and the genre. They have relationships such as written by and has a genre. In the property related to the book, you'll see plot embedding summary. This is similar to the summary, but in the vector form. This capability is something Neo4j's new version allows, as well as indexed vectors. These vectors represent the meaning of the text in this multidimensional space, creating layers of key nearest neighbors to enable efficient and robust approximate nearest neighbor search. In our database, we simultaneously have vectors that allows us to perform textual searches and find nodes and relationships associated with that node, which is extremely convenient for creating a chatbot. Okay, now let's move directly to loading data from our dataset into our database to achieve what we saw in the previous section. Conceptually, what we are doing involves extracting data from a table using the pandas library and, if necessary, pre-processing certain fields. For example, genres in our table are listed with commas and slashes, and we need to split them to create a list of genres and then record them as separate nodes. Ultimately, we create a dictionary to prepare the Cypher query with which we communicate with the database. We convert the text we want to turn into vectors using an embedding model, create a vector index in our database, and then step through the code. So we load all the necessary variables from the env file. These variables are for creating connections with the OpenAI model, API, and for connecting to our database, as well as the path where the dataset is located. We will use the similarity function to create the index with dimensions large enough to create embeddings. The larger the dimension, the more complex and accurate the vector structure can be, but this can also impact search time. I have created separate classes for creating a single connection to the model API and to the database. Now we create an instance for our data loader. Here we extract data from the table using pandas. Then we check if there are vectors in the table. Initially there are none, so we connect to OpenAI, convert each book summary into vectors, and record them in the dataset table. Now, if I need to reload data into the table, I will not need to create vectors as they will already be in the table. It should be noted that the text summaries are not large here, about a paragraph for each book. But if you were to upload the text of an entire article or entire book, it would be better to use chunks. If you're interested in this topic, let me know in the comments for the future videos. Now that we have the vectors, we check for an index and create a vector index. Let's look at the function and the Cypher query we use for this. We see that there is a special query in the latest version of Neo4j for creating a vector index. Next, we parse the genres and create a dictionary with the necessary data, and now we will load information about the books, their authors and genres, and then separately I load the vector data. We use the execute write built-in function and pass the function with the query to write the information. Here is a code to record information about books, authors, genres, and the vectors. Let's now turn our focus to the agent in our chat application. Our agent is structured in 3 layers, each adding functionality and intelligence to how it operates. So first layer implements the React model, meaning our agent is designed to reason and act based on the description of tools it can use. This React capability enables the agent to dynamically select the appropriate tool based on the user's query, ensuring that each response is both accurate and contextually appropriate. The tools housed in this layer are crucial for processing different types of queries efficiently. The first layer also has its personality, which we define through a prompt. This personality not only sets the tone of the agent's interactions, but also its limitations. For example, the agent is restricted to using only information from our database and cannot make suggestions beyond this scope. Alongside its personality, this layer includes the knowledge the model was trained on and access to OpenAI language model, and we use generative models here. The second layer is the Agent Executor. The Agent Executor class is used to manage the execution of an agent, controlling its life cycle and handling its interactions with the provided tools. By setting verbose true, we can track in the logs each tool the agent selects, providing transparency and insight into its decision-making process. Let's look at an example of how the agent functions when posed with a question. Here we see the agent deciding to use a specific tool based on the nature of the query. If the question is about a book plot, the agent might choose a tool that searches through vectors. For queries about a book by author or date, it might opt for a tool that generates cipher queries. The third layer of our agent, which involves runnable with message history and Neo4j chat message history, plays a crucial role in how our chatbot functions. Neo4j chat message history records our conversation within a session in the graph database. This allows us to see the current session, the last message, previous one, and more. Let's see how it works. So you can see it here, and as the application evolves in the future, this historical data can serve as the basis for a sophisticated recommendation system, for example, but now we can use it to increase the quality of our responses. So the agent is quite an interesting mechanism, and it needs to be supported by the language model we are using. Langchain shows each language models support the agent framework. The idea of an agent is that we provide a prompt that includes a persona, the history of our conversation, the tools, and the user's input. A sequence of runnable represents the agent. The agent operates in a cycle where each iteration either returns an agent action if a tool needs to be executed, or an agent finish, in which case we get the final response to the user. There can also be a list of sequences from tools known as intermediate steps. In our case, we have a fairly simple agent, so there are no intermediate steps for now. The chosen tool is executed by the program. After each cycle, the aggregated prompts is processed by the agent, and as a result of these cycles, we have literally one cycle here, but there could be significantly more. The LLM generates the final response. Let's take another look at our prompt. Here is the first cycle where the program decided to run a tool, and the second cycle where the agent returns the final response to the user. Okay, now we are ready to see how our tools work. First, we will see how the plot search is going. So Langchain also offers us ready-made abstract mechanisms for vector search in our database. First, we have a retriever to perform queries to the database for vector search. Here we pass all the necessary data, the database connection, the node name, the property name, and we define what should be returned to us. This includes embeddings, related data, and graph nodes. So, for example, we also retrieve the author. And as we remember, the author is another notebook. So we are searching through the vectors and get our embeddings, and we also can get the information about our books and our authors and so on. So next, we use Langchain's abstract tools to create a chain of calls. First, create retrieval chain. This chain takes in a user inquiry, which is then passed to the retriever to fetch relevant documents. Those documents and the original inputs are then passed to an LLM to generate response. Since our retrieve returns a document object, we need to convert it into a format that can be used in a prompt. So now we can use create stub documents chain. This chain takes a list of documents, formats them into a prompt, and then passes that prompt to an LLM. So this tool performs a vector search, retrieves the documents, converts the documents into context, takes the resulting prompt, and passes it to the LLM. And our second tool is for generating Cypher queries. Here we also have an abstract tool from Langchain, Graph Cypher QA chain from LLM. Each is chain for question answering against the graph by generating Cypher statements. The Graph Cypher QA chain class serves a functional role in querying graph databases, particularly Neo4j, using natural language questions. It utilizes an LLM to generate Cypher queries from input questions, executes them against the Neo4j graph database, and provides answers based on the query results. This utility allows users to retrieve specific data without needing to write complex Cypher queries, thereby making the data stored in the graph database more accessible and easy to interact with. It's important to craft a prompt that facilitates query generation, as complex queries can be generated more efficiently with examples. However, it's also crucial not to overuse the prompt's length to avoid a large number of tokens as they impact the cost. So, we have a very small piece of code that performs a significant function, transforming unstructured user text into a structured database query and retrieving results. That's it. You did an amazing job if you watched until the end, and I'm very grateful to you. Please leave a comment if you have any questions or clarifications, and feel free to share your experiences. Bye bye everyone!